Hi guys, this is Mrs. Uy,
And Miss Gray.
and we're going to do podcast 3.3 this afternoon, and it's all about mass of the atoms and
And about isotopes.
isotopes. So we're going to talk about isotopes and mass of atoms this afternoon. All
Okay,
right, I
piece of
hope
cake.
you're ready. All right.
Get your periodic table handy. You're going to need it.
Right. So isotopes. Let's talk about isotopes.
All right.
So isotopes are defined as atoms of an element that have
The same number of protons. Because an element will always have the same number of protons.
same number of protons
And electrons.
and electrons.
Because a neutral atom will have electrons that balance their protons.
Mm-hmm.
Right? But then they weigh a different amount because they have a different number of neutrons.
Okay, remember that, guys. An isotope has the same number of protons and electrons, but different number of neutrons.
Right. So here's an example with carbon that's used for carbon dating. There's two isotopes that are commonly found in nature. Isotope carbon-12
And carbon-14.
Right. And carbon-12 is much more abundant, but that makes it easier for us to spot the carbon-14 because it looks different. It's heavier.
It's heavier because it has
more neutrons.
more neutrons.
Right. In fact, it has 8 neutrons where carbon-12 only has 6.
So chemical properties of isotopes stay the same because they have the same number of electrons and protons. And they should know that because electrons is the one that, or electrons in an atom is the one that will give the property, right, Ms. Ray?
Right. So by chemical properties, we mean how it reacts with other things.
Yes.
And that's determined by the electrons.
Okay.
Okay, so if we have this kind of notation, what are we going to do with this? What does this tell us?
Okay, so this is
called isotope notation, and that top number,
this top number is known as the
mass number.
okay, let me just mass. Oops. This is tricky. That's mass number, guys, okay?
Yes, mass
All right,
number.
Mm-hmm.
so mass number of Mg2 plus is 24.
Right.
And then the number 12 below the 24 is known as
That's the atomic
that's
number.
the atomic number.
And so if you were to look on your periodic table, then you would see in the square for magnesium, there's a 12 there.
Okay.
Because its atomic number, 12, tells how many protons and electrons there are.
Yes. And then what about this 2 plus, Ms. Gray?
That looks like a charge. So a charge means that the electrons and protons are not balanced.
Yes.
And this means, because it's positive, we have more protons.
More protons.
Right.
Than
electrons. So if we had a chart like this, we could predict how many protons, electrons, and neutrons were in any of these things. You got a little black dot. Okay, good.
Okay.
So for hydrogen, if we were to look in the periodic table,
Right. Get your periodic table.
then we can find the atomic number.
And they should have the same table in their worksheet, in their packet, same as this table.
Yeah. So let's find one.
Here is hydrogen.
Right.
All right.
And so we're looking for the atomic number.
Atomic number of hydrogen is 1. It's right there.
All right. So let's go back to our slide, and we'll write in the atomic number for hydrogen.
All right. So atomic number of hydrogen is 1.
Mm-hmm.
What is the
atomic mass? Let's look on our periodic table.
It,
Do we just round to 1?
1.
Okay, so let me show how this packet thing works, though. For the atomic number, I just cleared that away. Sorry, that was 1. Atomic mass was 1.00797.
Shall I write the whole number?
Nah.
You don't. I don't need to write.
Nah. And then for the mass number, that's where we're going to round to the nearest whole number.
Okay.
So that would be just 1.
Just 1.
Okay,
And
so the
then?
number of protons we said was equal to the mass number.
All right. So that's going to be 1.
Mm-hmm.
And then the number of neutrons.
Neutrons, we have to subtract mass number minus atomic number.
Okay. So mass number is 1.
Mm-hmm.
And atomic number is 1.
Well, that's easy, because 1 minus 1 is 0.
Is 0.
Right. And then electrons
Is equal to
protons.
2 protons. So that's 1.
Yes. Because our atom, hydrogen, is neutral.
Yes.
The next one is not neutral.
Yes. It's not.
Our charge in the upper right tells us that electrons and protons are not the same.
Are not the same because this one is 3 minus, so meaning to say This one has more.
3 extra electrons.
3 extra electrons.
Yeah, the electrons are negative.
Okay, let's look at the atomic number of this element.
Okay.
Where is that? In the
arsenic
table?
is on the right.
It's right here.
Yeah. It's one of those metalloids.
Yes.
Okay, so what's the atomic number?
Atomic number, the number on top is 33.
Okay.
So we're going to write that down here, 33.
Mm-hmm. Great.
And then what about the atomic mass?
Oh, back to the periodic table.
Atomic mass is 74.02.
Okay, so we'll write 74.02 under atomic mass and then round to the nearest whole number for the mass number. So
and that's going to be 74.
74, right.
Okay.
All
number
right.
of protons for this element.
Protons equals atomic number.
Mm-hmm.
So 33.
So that's going to be 33.
Good. And then our
Why do I have all
electrons.
these zeros?
Oh, because we circled the arsenic.
Okay.
Yeah.
So number
Sorry
of
about that.
neutrons.
Number of neutrons is going to be mass number minus atomic number. So 74 minus 33. 41.
So 41. And then electrons.
Electrons are normally equal to protons.
Yes,
But not in this case.
Yes,
And we have a 3 minus, yeah?
Yeah.
That means we have three
Three
extra
more.
negative particles,
Yes.
which are the electrons.
Mhm.
So let's take our protons and add 3.
All right, so 33 plus
33 plus 3?
33 plus,
36, yeah. And
that's going to be 36 as the number of
as the number of electrons.
electrons.
Now, we're not going in order. They have a chart in their packet exactly like this.
Yes, but it's not the same as this one.
Right. We're doing some of them. The students will do all of them.
Yes, inside the classroom.
Right. Right.
All
Now
right.
tell me, why is there hydrogen there again? We already did hydrogen.
I know. So why is it? Well, look at this hydrogen right here. It doesn't have a charge.
Okay.
So meaning to say,
So this hydrogen is an atom.
yes,
The other
this
hydrogen
one
is a charged particle. We call that an ion.
an ion.
So we said that for isotopes, their protons and electrons are the same. Are
Yes.
ions the same as isotopes?
No.
No.
Ions are a charge,
Right.
right?
And isotopes differ by mass.
By mass. Look at the first example and see what's the difference.
Okay.
Okay?
So the atomic
hydrogen-
number has to stay the same.
Okay, that's one.
Right.
Atomic mass is still the same.
Right. Because it's not an isotope.
Yes.
It's an ion.
It's an ion. Mass
And
number.
Mass number is still the same, round to the nearest whole number.
Yes.
Okay. Protons, still the
Protons
same.
is still the same.
Because it's
that's
still
one.
hydrogen.
What about neutrons?
Okay, let's do mass number minus atomic number. 1 minus 1 is still 0.
0, 0.
Yep.
Now electrons.
Okay, so now we have a positive charge, which means our protons outnumber the electrons. We have more protons than electrons. That's how we get a positive charge.
Okay.
So protons are the positive things, right?
Yes.
So we better have an extra proton.
And
Is
extra
that allowed?
protons. Yes.
No, because if we had an extra proton, it would be helium.
Oh yeah, because this is hydrogen.
See, you got to watch me. I'm very sneaky, and
Yeah.
I'll make mistakes on purpose.
Yeah.
So that you can fix it.
Yeah. Thank you, Ms. Good.
You're welcome.
All right.
So a common mistake might be to add an extra proton because it's a positive
It's
charge.
a positive charge.
But that's not
in this
allowed
case,
in-
it's going to become
It's going to become a positive charge by giving
Yeah.
away an electron.
yeah,
So if we had one electron and we give it away, now we're left with none.
none. So electron in this case is
0,
0.
right? The only time you can add or take away protons is in a nuclear reaction. We're not talking about nuclear reactions yet.
Yes.
Yeah, only chemical reactions.
Yes.
Okay, I think this chart is done.
All right.
So if you have a positive charge, you take electrons away.
Mhm.
If you have a negative charge, you add electrons.
Exactly. Here are pairs of isotopes,
Mhm.
pairs A, B, C, and D. Now, question is, which of the following represents a pair of isotopes? They should know what an isotope is by now.
Okay, well, just to make sure I'm doing this right, I want to make sure.
Yes.
If it's an isotope, then their number of protons are the same.
Yes.
Okay, so do we have any pairs where the number of protons are not the same?
Okay. Number
let
of
me give
protons.
you your, yeah, so look at the P plus, and anytime they're not the same, let's cross them out so we
Okay,
don't count them.
P, that's
Right, so are those ones the same in A?
no.
Okay, that's not it then. That cannot be isotopes
Because
their
the
protons
first
are
one
not
is
the same.
6 and the second one is 7.
Okay, good.
What about letter B? Let's start with letter C.
Okay, we'll just go across. So there we have 6
6,
and
14.
14. No.
So C.
Absolutely not.
Not.
No. Okay.
What about number 7? The letter B.
7 and 7? That's
7P?
a maybe.
Yes, it should check.
Okay, so if the protons are the same, but now the next part is the neutrons have to be different from one another.
Yes.
Not different from the number of protons, just different from one another.
Yes.
So how many neutrons?
We have 13 and we have 14.
Okay, so those are isotopes.
Yes.
Now let's check part D because it doesn't say there's only
All
one, right? It
number
says,
of protons should be the same. So 6 and 14 is not the same.
Nope, can't be that. So we know the best choice is B.
Is B.
Great.
Okay?
So those are isotopes because protons are the same.
Yes, and
neutrons
are different. We need to know about the atomic mass or the weighted
average mass would be good. Yeah, the weighted average mass.
Atomic.
Right. So
mass.
on the periodic.
What does it mean?
On the periodic table, there's all of those decimal places after the mass number. So we know that's not a whole number. That doesn't represent just one isotope.
Yes.
Okay, so let's imagine that we have 100 people at a party. All right?
Okay.
So write down 100 people at the party. And suppose that we're going to weigh all of the people at the party.
Okay.
And so we have 90 people that weigh 50 kilos.
All right.
Okay, and then we have 7 people.
And then 7 people.
And they weigh 55 kilos. Okay, now we have 3 people left.
Okay.
And they only weigh 45 kilos.
Oops.
So if we were taking an average, would it be fair to add 50 plus 55 plus 45 and then divide by 3?
Add these 3 numbers and then divide it by 3.
Isn't that how we do average?
The average? I don't think so.
No, why not?
What do you think, guys? How are we going to get the average?
Well,
all right.
There's 100 people, so we have to divide by 100.
Divide 100?
Yeah, but what are we going to divide by 100? We can't
right.
just take those numbers you circled.
Yes. So what are we going to do is
take the abundance times the mass.
Multiply 90 by 50.
Right.
7 by 55.
Okay.
And then 3 times 45.
Right. And then we divide by 100
people.
Because we didn't only have 3 people there.
Yes.
We had 100 people there. So we need to represent the abundance of each mass.
Yes.
The mass number represents the number of protons and electrons. Sorry, the protons and neutrons.
Protons and neutrons.
But the weighted atomic mass is a weighted average of all the abundance
of the sample
a
of the
naturally
element.
occurring sample.
Yes. And when we're going to say weighted atomic mass, it reflects both the
abundance and the mass.
The mass.
Yes.
And to get that, we need to calculate.
Yeah.
Right?
And so we did some math here to find an average of the mass of people.
Okay.
Let's do the mass of...
so we have like only 2 steps that we're going to follow. I think there's only 2.
Okay.
All right. So first we're going to multiply the percent abundance of each isotope times the mass of each isotope. That's the first rule.
Right.
And the second one is find the sum of all the isotopes.
So we're multiplying first.
Uh-huh.
Then we're adding.
We're adding.
I can do both of those things. And I have a calculator.
Oh, because you have a calculator.
Right.
All right, Ms. Gray is going to help you. So let's take an example. All right.
Okay.
So we have 3 isotopes of oxygen. To multiply percent abundance by mass. So here is our percent abundance.
Okay, I'm on it.
So that's
99.759
0.759
times 16.
Is it going to be percent, Ms. Gray, or shall we move it?
I think we should change it to decimal form. Right.
So change percent to decimal, so it will become
0.99. Yeah.
7.
Move the decimal twice.
9 times
16.
Times 16.
You ready for your answer?
What's the answer?
15.96.
15.96.
144.
144.
Okay. Now normally we would not count all of those digits as significant, but in these problems, do not round until the very end.
Yes. Do not round until the very end. That's
okay,
very
so
good.
now let's take
Okay, the
that
second
next
one.
percent. Move the decimal twice
All
to
right,
the left.
so that's 1, 2.
All right, so
it
point
becomes
0, 0.
0.0037. Is it 0.0037?
Is it 2 0, 3 zeros?
3 zeros, I think.
Yeah, 3. Because we had one already.
0.0037.
I almost messed up. Times 17.
17.
Okay, you ready for that answer?
Yep.
0.00
0.00629.
629. Okay.
Okay. The third one is
all of these masses, by the way, have units of atomic mass units.
AMU.
Yeah, AMU. I think we talked about that in the first podcast.
Yes.
All right,
Okay,
now
move
move
this.
the decimal twice. So now we have 3 zeros.
0.0024
times 18.
times 18.
And I get 0.00432.
0.00432.
There you go.
And then
now we're going to find the sum of all of
this
our
number
products.
And then this one.
Right.
So 15.96144 plus 0.00629 plus 0.00432. What's the answer, Ms. Gray?
I get 15.972.
15.97.
205.
205.
Good. AMUs, of course.
All right. Right, AMU. AMU means atomic mass unit.
Okay, and let's have another click so we can see. That was our step.
Oh,
add the values.
Oh,
see,
very good.
We planned ahead to have that show up, and
So
we just
add
did
the
that
values.
step.
So what's the final answer in this, Ms. Gray? Are we going to round this off now?
Yeah, we can only keep 2 sig figs, it looks like.
2 sig figs.
So 16. Final answer is 16.
2 sig fig?
Yeah, 2 sig figs.
16.
Yeah, AMUs.
AMU.
For oxygen.
For oxygen.
Oh, good. Put a box around your answer.
Yeah.
Because that's the way I like it.
All right. And you're going to do more problems in that in your packet.
Of course. Right. Let's do another example.
Let's do another example.
Because this looks a little different than the last one.
Yeah.
It's just written a different way, and we want to show you that just because it's written differently doesn't mean we do anything different.
Okay.
We're still going to multiply the mass number
times
the percent.
All right.
Right, and then add up the products.
To get the final answer.
Yep.
Okay, so rubidium has 2 common isotopes.
Okay.
We have Rp85 and we have Rb87.
Okay.
Okay. If the abundance of Rb85 is 72.2%, so let's take 85.
And let's change that to a decimal, so 0.722.
0.722.
And we multiply that by
times
85.
by 85. And then what's the answer?
61.37.
61.37.
Right.
And then we have 87.
Okay.
Percent of abundance is 27.8, which means 0.278
right.
times 87 equals
24.186.
24.186. And then you're going to
add them all up.
All right.
And I get 85.
85.556. 556.
Okay, now I need everyone else watching us to get their calculators and make sure they can come up with 85.556. All right.
They can also check if we're doing the right thing.
Yeah, exactly.
All right. So 85.556. What's the final answer to sig fig?
Oh, how many sig figs are we keeping? Looks like 3 sig figs in our percents. So we'll keep 3 sig figs in our answer.
So
85.6 AMUs.
All right. So 85.6. Right?
Atomic mass units.
All right. That's my final answer.
Good. We're getting good at this.
Yay.
So if I change the way the problem looks, you'll still be able to do it, right?
Yes. Because it's very simple. There's only 2 steps that you're going to follow.
Okay. Well, let's see.
We
can
have
still
one
do it
more.
even if it looks different now.
Here is another example.
Right. And now we've shown each isotope as an individual particle.
Yes.
So how would we know the mass number of these particles?
Okay. So how are you going to get to mass number? You should know the mass number by adding neutrons and
And
protons.
Right? We can't add the electrons because they don't weigh anything.
Yes.
So it's just protons and neutrons.
So protons and neutrons.
All right.
What is the mass of the first isotope, or what?
Let's see. We have 82 plus.
So we have 82 plus 122. That should give you the mass number.
204.
204.
Right.
And then what about the second one?
Well, we still have 82 because it's still lead.
Yes.
All right.
But the neutron number is different. This one is 82 protons plus 124 neutrons.
Okay, so that's 206.
206. We're just adding protons and neutrons in here, guys.
Right.
So this one is still 82 protons.
I'm using my calculator. It's just one more than the one before. So
okay, so 207.
I'm making it way too hard. All right.
And this one is 82.
Mm-hmm.
And then one more.
And one more, 208.
This is a piece of cake for our student, Miss Gray.
I know, because I was making it so hard with my calculator to add one more.
Okay.
That's bad. Okay, so now take the abundance.
So percent of abundance for the first one.
Change your percents to decimals.
Okay, so move to decimal place. So this is going to be...
Okay, so 0.014 times 204 is our mass?
Mm-hmm.
Okay, I get 2.857.
This is the...
So that's our product of the abundance times
what's the answer?
The mass. 2.856.
2.856. So we're just multiplying these two numbers. This 24.1% change it to decimal. So move.
I almost multiplied by 24.1, but I need to have 0.241.
Okay, multiplied by 206. That should give you
49.646.
0.646.
Okay.
I hope I saw it. Then 22.1 should be 0.221.
Oh, more twos? No, 221. Okay,
221.
good.
Times 207.
Oh, I did it wrong.
Should give you...
Times 207. That is 45.747.
45.7?
Mm-hmm. 7.
52.4 will now become 0.524.
Okay.
Multiplied by 208, that should give you
108.992.
0.992. Now, the question says, using this data, calculate the atomic mass for each isotope and then calculate the overall weighted mass of this element.
Okay. So
we already got the atomic mass, right?
Right. And our last step is then just to add all of the products.
And that should give you?
So I got 207.241.
207?
Mm-hmm.
.241.
241 AMUs.
AMU.
You better have units after your numbers, or they are called naked numbers.
Oh, is this my final answer yet?
Yep. That's it.
That's it?
That's the overall weighted mass of lead. Oh, wait. You probably want to round for...
Yeah, that's what I'm saying.
Sig
All right. So the overall weighted mass is equal to 207.241 AMU, but we need to...
check for sig figs.
So
let's look at our percent abundance. How many sig figs did we have in there?
The original one?
Yeah.
This is 2.
Right.
This is 3.
Mm-hmm.
This
is
2.
You know what? We're adding things together, right?
Mm-hmm.
So we're counting decimal places.
Oh, yeah.
Yeah. All right. So
this is 3.
Keep one decimal place.
Keep one decimal place?
Yep.
So 207.2
AMUs.
AMU.
Those stinking sig fig rules.
Yeah, the number of sig fig we're adding.
Okay. That's how we do isotope problems. Great. I think that's pretty easy. And are we done now?
I think we're done.
That's it, folks.
That's isotopes and average atomic mass.
Awesome. Thanks, Mrs. Uwe.
Thanks, Miss Gray.